Hello. So for question 3, um, I was given a function over here, f of x is equal to x plus 2 cubed times x minus 3. I was given to it in factored form as well as in standard form. And I was asked to find and discuss the domain, range, intercepts, and behavior, first and second derivative, intervals of increase, decrease, max and mins, intervals of concavity, and inflection points. As well as a sketch of the final function. Now, I didn't do a hand-drawn sketch because it wouldn't have been as clear as this Desmos sketch. But anyways, this is the final graph, and I'm going to be going over every point, and then I'll be referring back to the Desmos graph to show the points that I just discussed. So to start with, I was asked to find the domain and range. So because this is a cubic function, as we can tell here from the 3 being the highest degree, as well as a polynomial with no restrictions, I can automatically tell that the domain and range is all numbers, xer and yer. As we can see here, this graph can keep going on forever. It won't stop, which means that the domain and range are both xer and yer. Then I was asked to find the x-intercepts as well as the y-intercepts. Now to find the x-intercepts, I basically made y equal to 0 and solve for the x's. Now, I did not do this algebraically, but you could. It's just, it would take a long time because there's an x to the, there's an x to the power of, as well as 8 times an x, which is two different terms, which makes it very difficult to do this algebraically. So what I did was I basically entered the equation unknowns mode on my calculator, and I plugged in the values of all these numbers. Basically got that there's an x value at 3 and there's also an x value at -2. And to find the y-intercept, you basically plug in 0 for all the x's, which is very simple. It all goes to 0, and then you're just left with -12. We can prove this on Desmos just by looking at the graph. The x-intercepts over here are at -2 and 3, and then we can also tell that the y-intercept is at 0, -12. Then I was asked to find the end behavior, and as I said before, we automatically knew that this was a cubic function with no restrictions. So we knew that basically the general shape of it looked like this, like the cubic function. That's just the general shape. So we can tell that the end behavior as x approaches -infinity is -infinity, and then as x approaches infinity, it's infinity. Just as we can see here, as x approaches -infinity, it goes down to -infinity, and then as x approaches infinity, it goes all the way up to infinity. And then we can see this on our graph in Desmos. It can keep going all the way to the right, as well as all the way. As x approaches all the way to the infinities, it will go all the way up to the right to the infinity, and then as x approaches the negative infinities, the y values will go down to the negative infinities. Now the first and second derivative, quite easy to find. Just use the power rules. So the first derivative is 3x squared plus 2x minus 8. I basically got that by using the standard form of the function, not the factored form. And then using power rule, basically I dropped the 3 over here, and then became a 3x, and then I took a 1 out of the degree, and then that turns into a 2. And then I just followed the same pattern for all the numbers, so that's 3x2 plus 2x minus 8. And then for the second derivative, follow the same power rules, drop that 2 to the 3, turns into a 6, minus 1 from the 2, so it disappears, and then just drop the x, and then it got rid of the -8. And then we're left with the second derivative of 6x plus 2. Moving on, it was asking me for the intervals of increase and decrease. So to find the intervals of increase and decrease, what I did was first I found the first derivative, and I wanted to find all the I wanted to find when the first derivative equal to 0. So I was basically finding the roots of the first derivative. Again, I did not do this in my calculator just because, I didn't do this algebraically. I did this in my calculator just because I found it easier to use the unknowns / equation mode and plugging in the numbers just to get, and then they'll give you the x values. I just found that easier, but you could do this algebraically. Anyways, after you find the roots of your first derivative, which in this case is 1.3 and -2, you have to do something called an interval chart, which is what I've done over here. And you're basically taking intervals intervals that match the x values you were given. So I used the intervals negative infinity till -2, and the -2 represents the first root that we found, or the second root, I guess. It doesn't really matter. Or actually, you just want to start with the lowest x value. So the smallest x value should always come first. In this case, it's -2. And then I did an interval of -2 to 1.33, as that's the other x value, and we know that both of these values are on the f prime of x graph. And then I did 1.33 all the way to infinity. My apologies. Then after that, what I did is I plugged any number between -infinity to -2, like any number in between this interval, like in between each interval, into the first derivative. And then if the number was a positive, I would write a positive here, and if it was a negative, like in this case, when I plugged in -1 into f prime of x, I got a negative, so I put a negative here. So what this represents, we know as a rule that when the first derivative is positive, the original function, the f of x, will be increasing on that interval where the first derivative was positive. And then on the intervals where the first derivative is negative, we know that the original function, the f of x, would be decreasing. So that's how we can find the intervals of increase and decrease. And we can see this on the Desmos graph, as we can see that from -infinity to -2, so -infinity all the way to -2, it's increasing. And then from -2 all the way to 1.33, it's decreasing. And then from 1.33 all the way back to infinity, it goes back up to increasing. Now, after doing the interval graph, it's actually really easy to find the max and min, since we know that -2 is where the graph basically shifts from increasing to decreasing. When a graph shifts from increasing to decreasing, we know that that's a local max, and when a graph shifts from decreasing back to increasing, we know that that's a local min. And you can basically imagine that in your head. Like, just picture something going up and then going back down, that creates a max, and then picture something going down and then goes back up, that creates a min. So we know that the local max is at -2, and that the local min is at 1.33, the x value. So it's really simple to find the local max and mins. We just plug in the x values into the original equation. So you plug in the -2 for f of x, and you plug in 1.33 for f of x. And you'll basically get a final answer of a local max of -2, 0, and a local min of 1.33 repeating, -18.5. Roughly, this is a rough estimate because we used 1.333 as being one of our x roots. And we can prove that over here. Our local max is actually at -2 and 0, and then our local min is at roughly 1.33, -18.519. Well, I guess that's the exact number because this is the Desmos graph. And then for intervals of concavity, what I did was I knew that, I first found the second derivative, and I knew that to find a point on the second derivative's graph, I just knew that when the second derivative equals 0, like when the second derivative equals 0, that is where the point of inflection is. So I made the second derivative equal to 0, and I solved for the x value, and the x value I got was -0.33, and this represents the x value of the point of inflection on the original graph. So after that, I did another table, like another interval table, to find where f of x is concave up or down, and I used the same thing as we did in the first graph over here, except I plugged in my interval numbers into the second derivative, not into the first derivative. And then if I got a negative number, I put a negative, and if I got a positive number, I get a positive. And a negative number on the second derivative basically represents a concave down interval on the original function, and then a positive number on the second derivative will represent a concave up interval on the on the original graph. And you can basically use any number between -infinity to -0.33, because like this is your interval that you're looking for, so you can use any number in between those numbers to plug into f2 prime of x, And the same thing with here, you can use any number from negative 0.33 all the way to infinity. Now, to find the final thing, which was the inflection point, as I said before, we know that negative 0.33 is actually the x value of the inflection point on the original graph. So very simple to find the y. All I did was I subbed in x into the original function, which is f of x. So I basically turned f of x into f of negative 0.33, plugged in all the x values, and I roughly got negative 0.33 comma negative 9.3 as being the point of inflection. And we can prove that here on the Desmos graph. Unfortunately, for some reason, it wouldn't pick it up, but the point of inflection is roughly around here, and we can see that that's roughly around negative 0.33 and somewhere around negative 9 over here. Anyways, that is, I believe, yeah, that is it for this question. I apologize if it was lengthy. I tried to put in as much information as I can. Thank you so much. I'll see you with the final question.